Welcome to a screencast on energy basics that are relevant in chemistry. All chemical and physical processes involve changes not only in matter, where atoms or ions break bonds, rearrange, form new bonds, form new substances, but they also involve energy changes. For example, acetylene, C2H2, is a gas that can undergo combustion, and when it does, when it burns, it gives off heat. In fact, as shown in this picture, it gives off so much heat that it can be used to weld together railroad ties. Processes like this that give off heat are called exothermic. Now, on the other hand, we can have processes such as the one that occurs in a chemical cold pack, where solid ammonium nitrate dissolves in water, and when that happens, when the solid ammonium nitrate dissolves in water, it absorbs heat. And you can feel this if your hand is nearby. Your hand's going to get colder because heat is being absorbed from your hand by the dissolving process of ammonium nitrate. And processes like this that absorb heat are called endothermic. Now, when we deal with any kind of energy change in a chemical process, it's good to have a little bit of background information. So first, a couple of things pertaining to energy in general. And one way of defining energy is it's the capacity to either supply heat or to do work. And we can talk about energy in a number of different categories. And another common classification is to talk about energy as being either kinetic energy, the energy of motion, or potential energy, stored energy that is potentially available for use. So a moving car has kinetic energy, the energy of motion, and a cheeseburger has potential energy because there's energy stored in the cheeseburger that after you eat it can be used to keep you warm, supply heat, or to provide energy for you to be able to do some sort of work. Now, another thing we know about energy is that it cannot be created or destroyed, but it can be converted from one form to another. This is called the law of conservation of energy. It's also known as the first law of thermodynamics. And an example of that is an athlete walking up or climbing up a ladder to a diving board. And while climbing up the ladder, the athlete is converting stored energy in his or her muscles into energy of motion moving up the ladder. Once he or she is at the top of the ladder and on the diving board, now there's stored energy due to the position above the surface of the water. And when the diver dives off the board, that stored energy due to height above the water can be converted into kinetic energy or energy of motion. When the diver hits the water, some energy is used to push the water away so the diver can enter the water. Some is transformed into sound or splash. But in the whole process, no energy is created, no energy is destroyed, but energy can be converted from one, or is converted from one form to another. Now, we will often deal with heat, which is the transfer of thermal energy between two objects that are at different temperatures, and thermal energy is the kinetic energy of molecular motion. So molecules are moving. If they're moving fast, they have a high kinetic energy. If they're moving slowly, they have a low kinetic energy. And in fact, to be a little more specific about this, if we have an object that is at a low temperature, and we would normally say it's a cold object, this is because its atoms are moving slowly. So here are some atoms making up the substance, not moving very fast. Now, if we have an object that's at a high temperature, and we would typically say that it is hot, what this means is that its atoms are moving quickly by comparison. So here is a high temperature or hot object, and its atoms, its molecules, are moving at higher speeds, on average. Now, heat always flows from a higher temperature object to a lower temperature object. In other words, it flows from something that's quote-unquote hot to something that's quote-unquote cold. And this we find to always be the case. So here's a high-temperature object, here's a low-temperature object. Heat flows from the high-temperature object, so its molecules lose heat, so to speak, and become slower on average. The cold object absorbs energy, absorbs heat, its molecules become faster on average, and this process will continue until the temperature of the two objects are the same, or we would say until thermal equilibrium is reached. Now, when we deal with chemical reactions, which is what chemists are often interested in, energy is either overall released or overall absorbed, depending on the net energy change for breaking bonds in the reactants and forming bonds in the products. In some cases, more energy is needed to break the bonds in the reactants than is given off forming bonds in the products. In other cases, more energy is given off forming bonds in the products than is needed to break bonds in the reactants. And we'll consider both of these cases. One example of one of these processes is the combustion of acetylene, which we talked about earlier. And when 2 moles of acetylene, C2H2, undergo combustion, when it burns, it actually produces 2,600 kilojoules of energy. Here, the energy produced is written as a product because it's actually energy that's given off, and it is therefore an exothermic process. Now, the other example we looked at before was ammonium nitrate solid dissolving in water to make ammonium ions and nitrate ions, and this process requires energy. It needs to absorb some energy, and in fact it needs to absorb 25.7 kilojoules of energy to dissolve 1 mole of ammonium nitrate, and in this case we have a process that is endothermic. Energy is absorbed, and we could think of energy or heat as essentially being a reactant. Now, we often diagram this, show it pictorially. For example, if we graph energy on the y-axis, and initially we have some reactants with a certain amount of energy, and then the reaction takes place, and we have products at a lower energy, we often use the x-axis for progress of reaction, and so from left to right, we have reactants turning into products. And in a case like this, where the products have a lower energy than the reactants, then we have what's occurring here. When energy is given off in a chemical reaction, the products are going to have less energy than the reactants, and the products are therefore more stable than the reactants. And of course, this is a process that is exothermic. Energy is given off. Now, the other way, the other type of process, we have reactants with a lower energy, products have a higher energy, and in this case, when energy is absorbed in a chemical reaction, the products will have more energy than the reactants, and the products are going to be less stable than the reactants. And this is what happens when we have an endothermic process. Now, chemists usually deal with these sorts of energy changes in chemical reactions using something known as enthalpy, which we symbolize by the capital letter H. And we're going to deal with enthalpy changes, or delta H, and every reaction has an enthalpy change or a delta H that's associated with it. Enthalpies are just as important a part of the chemical reaction as the reactants and products, and they're treated quantitatively in the same way as the amounts of substances involved. So just like amounts of products and reactants are proportional to how much reaction takes place, so is the amount of heat or the amount of enthalpy change proportional to the amount of reaction that takes place. And on a technical note, enthalpy is actually heat flow at constant pressure, and we normally perform reactions at constant pressure, so most of the time, kind of loosely, we can think of enthalpy of reaction as essentially the heat for the reaction or the energy change for that reaction. And going back again to our example of acetylene undergoing combustion, it produces 2,600 kilojoules, and we often write this instead as delta H for this reaction, the enthalpy change for this reaction, is negative 2,600 kilojoules. And all this means is the negative sign indicates that 2,600 kilojoules of energy are given off. And for the endothermic process, the dissolving of ammonium nitrate, which absorbs energy, we can rewrite this process with a delta H value, and the delta H value for this process is positive 25.7 kilojoules, and that just means that 25.7 kilojoules of energy are absorbed for this process to take place. So exothermic reactions will have a negative delta H value, negative enthalpy change. Endothermic processes, endothermic reactions will have a positive enthalpy change, or positive delta H. And that's it for the Energy Basics screencast.